So, how does a robot actually know where it's supposed to go? Usually we just give it a very specific static target, a picture or coordinates. But what if there's a much, much better way? Let's dive into some really fascinating research that is completely rethinking what a goal even means to an AI.
Okay, let's start with a super simple scenario. We have a robot arm, and its only job is to place a block right on this specific spot. Traditionally, the way we do this is to give the AI an exact picture of that final state, or maybe the precise coordinates of the target location. Seems simple enough, right?
Well, here's the problem. The real world is messy. What happens if a shadow suddenly falls across the target or the lighting in the room changes? All of a sudden, that picture of the goal is totally different. The AI gets confused and the whole task can just fail. This kind of brittleness is a huge, huge challenge for robotics.
To solve this, researchers proposed a really radical shift in perspective. Think about it this way. How would you define the location of the Eiffel Tower? The old way is to just give its exact GPS coordinates, a single static point. But the new way, you define it by its relationships, how long it takes to get there from the Louvre, or from the Arc de Triomphe, or from Notre Dame.
And this brilliant idea, this relational way of thinking, is the core concept behind what's called dual goal representations. So instead of defining a goal by what it looks like in a single moment, you define it by its relationship to everything else in its environment.
Now, the key metric for these relationships is something called temporal distance. And honestly, the concept is beautifully simple. It's just the shortest possible time it would take for the AI to get from any possible starting point to that final goal. Just think of it as the AI's travel time. This whole approach is built on a really deep, almost philosophical idea, which the researchers actually mentioned was an inspiration for their work. It's the idea that you can understand something not by what it is in isolation, but by how it connects to everything else around it. So here's the crucial switch. We basically throw away that static picture of the goal. And instead, we give the robot this rich, dynamic map of all these temporal distances. The goal is no longer just a single point, it's this whole landscape of travel times. Now, according to the theory, this new way of seeing things gives the AI two incredible superpowers. First, sufficiency. This map of travel times contains literally all the information the AI needs to figure out the best possible path. And second, and this is the big one, noise invariance. Because the travel time doesn't change just because a shadow appears, the AI can completely ignore those irrelevant visual distractions. Okay, that all sounds absolutely amazing in theory, but does this relational approach actually make for a smarter, more effective robot in the real world? Let's take a look at the experiments and find out. First off, how do they even build one of these things? Well, it's a three-step process. First, the AI learns to approximate that map of temporal distances between all the different states. Then, it uses that map to build the new relational goal representation. And finally, it trains its actual decision-making policy using this much, much richer definition of a goal. For their first test, they used a classic puzzle called Lights Out. Now, the original method, which you see in the first bar, learns pretty slowly. But the dual representation method, that second bar, wow, it learns dramatically faster and hits a much higher success rate. A really clear win right out of the gate. But, a simple puzzle is one thing. The real test came on the OG bench, which is a suite of 20 really challenging robotic tasks. We're talking everything from controlling complex humanoid robots in a maze to manipulating multiple objects at once. And the results were seriously impressive. If you look at the average success rate across all the state-based tasks, the original method scored a 34. The new dual representation method is scored a 41. That is a significant leap in performance across a whole wide range of really difficult problems. Okay, so it performs better, that's great, but what about that other promised superpower? Is it really more robust to all that noise and distraction we talked about? So to test this, the researchers basically tried to trip the AI up on purpose. During the evaluation, they added a bunch of random visual noise to the goal states. You can think of it as the digital version of flickering lights or passing shadows, just to see how the different methods would cope with these unexpected distractions. And yeah, the results were conclusive. Across multiple environments, the dual representation AI proved to be consistently more robust. It successfully navigated to its goal even when that goal was partially messed up by all that noise, proving the theory really does hold up in practice. So, the big takeaway here is that we're not just looking at some clever trick to make a robot slightly better. No, this feels like a really fundamental shift in how we might teach an AI to understand what its objectives even are.
We're moving away from teaching AI to see the world as just a collection of static, isolated snapshots. And instead, we're teaching it to see a dynamic, interconnected web of relationships where the meaning of any one thing is really defined by everything else.
It leaves you with a pretty big question to chew on, doesn't it? What if the secret to building more general, more adaptable, and truly robust intelligence, not just in robots but beyond, isn't just about feeding it more and more data, but about teaching it to understand the deep relational fabric of its world? Definitely something to think about.